thank the organizers of the conference for giving me this opportunity to speak in this conference. I've been really enjoying the talks for the last 3 days. Okay, so I'm going to talk about a Spin-1 version of the random energy model. So I know in the audience there are a lot of people who know a lot more about random energy models than me. I'm kind of new to the topic, but I think maybe we have something to say here. This is a work which I have done with Matteo Marsili, who's at ICTP-3SA, and I think I should also add an acknowledgement which I forgot to add here. My visit to ICTP was supported by the Simmons Associateship, by the Simmons Foundation for ICTP. And the references for the work are these. So I will mostly be talking about the first reference, but since there is some connection, towards the end, if time allows, I'll briefly also discuss some results of our previous work, which deal with a slightly different kind of a disorder. Okay, so my outline is very brief because there have been there were some talk, I think, on the first day on p-spin models. So I'll quickly recap the random energy model, the original random energy model with a very simple and beautiful exact freezing transition. Then I'll come to our work, which is kind of a simple extension where we, instead of taking the icing spins, take the spin-1 spins to be spin-1. That is, they have 3 states. And there is also a similar work which was done by Motishaw in 1986, which is slightly different than the way we define the spin-1 random energy model. So I will try to talk about both of them. And in the end, I will also hopefully talk about the other kind of disorder, which is the random field spin-1 model. So for the sake of completion, I have just added one slide, that because the idea of classes starts with the idea of the Sherrington-Kirkpatrick model. So I think in this audience I don't need to say much about it, but still just for the sake of completion. So this is a model which is like a generalization of the Edwards-Anderson model, in the sense that now the Sherrington-Kirkpatrick defined it on an all-to-all graph, and the JIJs are the couplings, which are the random couplings which are quenched, which are taken from a Gaussian distribution of this kind, and the spins SIs are ±1 spins. So there is a frustration in the system because of the fact that these couplings JIJs, they are not the same for every interaction, but they vary depending on they vary from one pair of interaction to another. So long ago, and there have been like more details to the model, to the phase diagram of the system. The phase diagram of the system was shown to have a low temperature spin class phase, which as one increases temperature goes to a paramagnetic phase, and at low temperatures it was also shown that it goes to a mixed phase, and from that it goes through a Almeida-Thouless line to a ferromagnetic state. So this is the phase diagram of SK model, which is known since a long time. So let us come to Derrida's random energy model. So to derive the random energy model, one considers the generalized SK model with p-spin interaction. So the Hamiltonian now contains interaction between p-spins, and the couplings now are taken from this distribution. Okay, so in this case, then one can show that using the central limit theorem that the energy of any configuration actually has a distribution which looks like this. And interestingly, when one takes the limit p going to infinity, one can also show that these the distribution, these EI, the energies are IIDs, because the PE1 E2 is just a product of PE1 and PE2. So based on this, the Derrida defined the random energy model as a model with 2 power n energy levels, and in the original model, the energy levels have a Gaussian distribution with mean 0 and variance n by 2, and these E are the independent random variables. The model is very easy to solve. The entropy per spin has a very extremely simple expression, and it is just log 2 minus E square. So one can see that the moment the average value of E is greater than the square root of log 2, entropy essentially is 0 or negative or subextensive, which means there are essentially no configurations with energy larger than this. And if we go from the energy to temperature regime, this converts the EC being square root log 2 converts to the glass transition temperature of TF, which is given by this. So based on this, so the system for T less than TF has entropy 0, so it's a glass, and for T greater than TF, it's just a gas because there's no magnetization in the system. This is the susceptibility plot. Not just that it had a frozen phase below a finite temperature, the random energy model also had showed other feature of the glasses, namely that the magnetic susceptibility in the glass phase was constant and it decayed outside the glass phase. So one could see that though it's an extremely simple model, exactly solvable, it did capture a lot of features of the glass. And I'm not going into the history of random energy model. One can find a lot of work. So since then, one doesn't have to go and motivate it from the Sherrington-Kirkpatrick model. These three are enough to define the random energy model. And in fact, many different probability distributions other than the Gaussian have been studied. And the glass transitions have been, and other features have been found in them. There is also an extension of the random energy model, which is known as GREM, which also incorporate ultrametricity. But we will not go to GREM, we will only be talking of REM. So how do we go about the Spin-1 random energy model? So now we have Spin-1, so the spin can take 3 values, plus, minus 1 and 0. So we have a system with 3 power n configurations, and we want to build a probability distribution PE, which such that the energy can be drawn from this, and energy is a stochastic IID variable. So we notice that if we have spin-1s, that is the spin can take 3 values, plus, minus 1 and 0, in that case one can look at the entire graph as being built of one click and many disconnected paths, in the sense that whenever a spin is 0, that spin will not contribute to the interaction. The only spins which will contribute to the interaction term are the spins which are plus minus 1. So we can look at the model as something which has a click of say q plus minus 1 Ising spins and 0 spins. So the only contribution of the random energy would then come from this click. Okay, so that is what we take into consideration. So based on this, we divide the set of configuration by the number of Ising spins the configurations have. So a configuration with, so the number of configurations with q Ising spins, it's easy to see, are so many. Now there's an additional factor one adds, which is the crystal field. So for every plus minus 1 spin, we add a crystal field which kind of tells whether the system has chosen a plus minus 1 spin, the Ising spin, or the 0 spin. If that is the case, then for such configurations for which q is fixed, the crystal field contribution to the energy is just delta q. Now, based on this, we assume that if we stay in this subspace of configurations, let the energy of this subspace then has an average around delta q, and it is also a stochastic variable which is distributed like a Gaussian, but now we only have q Ising spins. So this is the form of the distribution in that case. Based on this, one can write the full distribution, which would then be by summing over all values of q, and which would look like this. So now we have a Spin-1 model which For the time being, we have called it crystal field random energy model. So this is a model, Spin-1 model with 3 power n IID energy levels, and their distribution is given by this probability distribution. So now we will work in the microcanonical ensemble. So we take the log of the density of states as the entropy of the system. So this is the density of states, and one can then go to the large n variable, and instead of working with capital Q, capital E and capital N, I am going to work with small q and epsilon, and one can write, then one can do the, use the Stelling's approximation to write this density of states like this. From this, there's a bit of algebra involved. One finds that the entropy as a function of energy is given by this expression, and here the Q star is actually the saddle point of the integral I showed you on the last of this integral. So Q star is the saddle point of the integrand of the function f of the integral, so which is found from f, and this Q star is connected with the value of epsilon via this relation, and if you plug in this relation, the entropy as a function of epsilon and the crystal field delta is given by this expression. From this we can go, it's easier to work if we get the expressions as a function of temperature. So we can get entropy as a function of temperature and the free energy also as a function of temperature, and the typical value of Q. So small q is the fraction of plus minus 1 spins in the system. So one finds that that has an expression which looks like this, and you can see in the exponential there is a 2 competing terms. So one can see that there will be some kind of a change in behavior of the system, and these are the expressions of entropy and free energy for this model. And there another detail is that there is actually a temperature Tf delta where this entropy, this function actually becomes 0. So by equating this to 0, we can find what is the freezing temperature, which is a function of delta. Obviously, when delta goes to minus infinity, we should get back the Ising original REM. We do get back the original REM when we take delta going to minus infinity. For any general delta, the freezing transition happens at a temperature Tf, and if you look at the lowest graph, which is h equals 0, I'll come to the other 2 plots little later. So if you look at that, that gives the freezing temperature for the system as a function of the crystal field. Interestingly, now if we look at specific heat as a function of temperature for different deltas, this is where we find something non-trivial. We find that for around delta greater than 1.5, besides having this jump at the glass transition, there is also a bump in the specific heat which occurs at a higher temperature. Okay, so this is what we learned by just looking at the pure model. Then we introduced the external field to study the more details of the system. In that case, the probabilities then are given by this, and the entropy is given by this, where Q star and M are connected by these 2 set of coupled equations. So we have to solve these in order to get Q star and M and get the S for the system. Again, it's easier if I write everything in terms of T. So when one does that transformation, the entropy as a function of T for this model in the presence of external field looks like this, a nice simple expression with the value of Q star and the M. So there's an error, sorry, there should not be any F here. It should all be just M equals Q star times H by T. I copied the wrong expression, sorry. So this is the entropy of the system with the value of Q star, which is the fraction of plus minus 1 spins, and M, the magnetization, being given by this. And the free energy has the same form as before, which is just this, just that the Q star has now the information of the field. Now using this, we can again find the freezing transition, and just like the original random energy model, the freezing transition happens into a mixed ferromagnetic state also here, and these two lines are for H equals 1 and 2, just to show how the freezing temperature changes as we change H. We can also get the Almeida-Thouless lines. We were hoping we will see some non-monotonicity, but we didn't see. So they are just kind of similar to Almeida-Thouless lines in the random energy model, and they look like this. Now, there's something little interesting that we see when we now look at the magnetization. So here I have fixed the external field, and I'm looking at magnetization for different crystal fields. And just like if you recall, I said when the magnetization was 0, the crystal field had a bump. Here even the magnetization shows an increase with temperature in the region where earlier it was just a simple paramagnet. So if delta is large enough, we again see that the magnetization can increase with increasing temperature. We explore it a little bit more. So here you can see the 3 plots where now the crystal field is fixed. In the previous plot, the magnetic field was fixed. Now the crystal field is fixed, and we can see as we increase H, it seems that for high enough H, this I don't want to call it re-entrance because there is no transition, but this increased order seems to vanish. So with little thought, we could come up with actually a very interesting, very simple explanation of why this is happening, a kind of little trivial. So if we take m plus q by 2, that is the number of +1 spins. So one can see at the freezing transition, if the number of these +1 spins were less than 1 by 3, which is their value for t going to infinity, then then their number always decreased to go to the t going to infinity limit. But if it was less than that, there is a time when it increases, and in this time -1 spins are also increasing, but if their rate turns out to be slower than the increase of +1 spins, perhaps because of the magnetic field, and hence it gives rise to this increase in magnetization. Whereas one can see if at the glass transition the number of +1 spins was much more than 1 by 3, then they just simply decayed, and in that case even the magnetization just had a monotonic decrease. And so we also looked at the magnetic susceptibility, and there also it's consistent around the same values of lambda. Susceptibility also shows a peak in the high temperature region. So this is the first Spin-1 model I wanted to talk, and now I'll briefly talk of the work of Peter Mortishaw, which is the 1986 work, and this is based on the Ghatak-Sherrington model. So Ghatak-Sherrington model is a model with Spin-1 particles, and it actually spin can take value -s to s, but we are going to only consider Spin-1. So it is just like the SK model, but now since we have Spin-1s, we have a crystal field term. So what I have been calling delta, I have called it D here because in the original papers they used D instead of delta for the crystal field. And this model is known to have a phase diagram as a function of temperature and the crystal field. This delta, you can forget, this delta has nothing to do with the delta I've been talking about. It is just some constant where there is a transition between spin glass and a paramagnet, which is continuous at higher temperatures and which becomes first order at lower temperatures. Okay, so now if one takes a p-spin generalization of the Sherrington-Kirkpatrick model and again do the central limit theorem, one can again come up with a resultant random energy model. And though for finite p the distribution of energy is Gaussian, the moment you take p going to infinity, there is something interesting going on in the sense that this limit makes the distribution have two different forms. That is, then when the all the spins are, when Q is n, all the spins are plus minus 1. In that case, the distribution is Gaussian with mean n delta Q. There should have been a Q here. I missed it. So it is just like what we took, but we had a Q here, but here there's no Q because Q is n. And when Q was less than n, it was just a delta function, which roughly says that there's a Q value which gets picked up by E. Besides that, it's almost like a free gas. So in this case, they also had a phase diagram, and the phase diagram looks like this, where there's a spin glass and there's a paramagnetic phase, and there are two kinds of paramagnetic phase, but this is the spin glass, which always happens at the same temperature, which is the temperature of the Derrida's random energy model or the Ising random energy model. So I will not go into more details of this model. There have been replica calculations also of this model. So you can look at the original paper if you are interested to look into that. And we are also studying it further because I think there are few things which are unexplored about this model, and to make more comparison with our model, and if there are other possibilities of a Spin-1 random energy model, we are still looking at this model in some bit of a detail. So I have 3 minutes, so I will switch the gear now. So I was talking of the random bond interaction till now, but now I will talk of a different kind of disorder interaction, which is the random field interaction, disorder interaction, and that also in the case of spin-1s. Actually, this is the one I have been studying for a while, and somehow this is the one which made us also try to think of the random energy model. So in this case, we have a nice ferromagnetic coupling between the spins. We have a crystal field and we have a quite...
Long live India and France friendship.